So this is Leaving Cert 2025, Paper 1, Question 4, and we're given this complex number and told to write in the form a plus bi, where a and b are real numbers. So basically what we need to do is we need to get rid of this complex number on the bottom, and one way we can do that is by multiplying the top and the bottom by the conjugate for plus 5i. So just changing the sign from a minus to a plus. And the reason we can do this is because the value of this fraction is just 1, so we're just multiplying the original thing by 1, so it doesn't actually change anything. But you'll see that it works now. So we'll have 2 plus 3i times 4 plus 5i, because when we're multiplying fractions, just top by top, bottom by bottom. More 4 minus 5i, and 4 plus 5i. Then we just multiply out the brackets, we'll get 8 plus 10i plus 12i plus 15i squared, all divided by 16, and we'll have plus 20i minus 20i minus 25i squared. And you'll notice that these two terms in the middle cancel, and the reason for that is because this here is a difference of two squares, so we end up just having the first thing squared, so 4 squared gives us this 16, and then we'll have minus, and then 5i squared gives us 25i squared. So that's the reason that they cancel out, and it's the reason that it works, that we're going to get rid of all the things with an I in the denominator, as you'll see now. So on the top we're going to have 8 plus 22i, and then I squared is minus 1, that's given in the question, it's kind of the definition of I, so plus 15 times minus 1. All over 16 minus 25 times minus 1, again for the I squared. And then what we're going to have is we're going to have 8 minus 15 will give us minus 7 plus 22i over, and then a minus and a minus makes a plus, so we're going to have 16 plus 25 will give us 41. Now we want this in the form a plus bi, so we can just split this fraction up if I bring it over here. So we'll just have minus 7 over 41 plus 22 over 41i, and that is our answer. Next, we're asked to use De Moivre's theorem and this expression right here to prove the following statement, the equation down there, as you can see here. So first of all, you need to find De Moivre's theorem. It's on the algebra page on page 20, and you can see it here. This part here is not really relevant to the course anymore, so you can ignore that. So I'm just going to write down the rest of De Moivre's theorem. So here's De Moivre's theorem written down, and you might not be too sure what to do here, but I suppose one thing you could think of doing is see how they give you the 2 in the power there. So we might think to set n equals to 2, so that we get 2's in the power. So if we do that, we will get this whole thing, and we're going to have that squared, and that'll be equal to r squared times cos 2 theta plus I sine 2 theta. And now what we can do is we can use the rules of indices, that if we have two things multiplied together to a power, we can just put the power on each of them individually. So each of these two things multiplied together. So we can have r squared times cos theta plus I sine theta squared, and that'll be equal to the right hand side. And then we can divide both sides by r squared, because we don't want an r in our answer, as you can see. So then we're just going to have basically cos theta plus I sine theta squared will be equal to cos of 2 theta plus I sine of 2 theta. And now what we can do, again, it's not really too obvious what we can do, but we could just multiply out both sides, because we need to get cos 2 theta by itself, but you can see on the left hand side it doesn't really look like anything useful. So let's just multiply out that bracket, so we can just write down the bracket twice and just multiply it out as normal. And that's just going to still be equal to this stuff. We can't really do anything with the right hand side. So let's multiply out the left hand side. We're going to get cos squared of theta when you multiply it out, and then we're going to get 2I sine theta cos theta, and then we're going to have plus I squared sine squared theta, and that'll be equal to the stuff on the right hand side. And we can just do one small bit of simplification. So remember, I squared is minus 1, so we can write this, if we collect all the real stuff together and all the imaginary stuff together, because they're kind of two distinct things, we'll have cos squared theta minus sine squared theta as kind of one entity, plus, and then we're going to have 2 sine theta cos theta multiplied by I, so that's our imaginary part, and on the right hand side we have cos 2 theta plus I sine 2 theta. So basically, the real part on the left hand side has to be equal to the real part on the right hand side, and the imaginary part on the left has to be equal to the imaginary part on the right. If that's not too obvious, I guess one easy way to see it is if you had like 2 plus 3i equals a plus bi, it should be pretty obvious what a and b are, because, you know, the real part and the imaginary part are quite separate. So here, looking at what we want cos 2 theta, so that's the real part, so the real part on this side has to be equal to the real part on this side. So you can say the real part of the left hand side has to be equal to the real part of the right hand side, which gives us that cos squared theta minus sine squared theta is equal to cos 2 theta, which is what they asked for. In part C, we're asked to use de Moivre's theorem to solve this equation and give answers in the form c plus di. We want two answers, and c and d should be real numbers left in third form. So basically, remember that de Moivre's theorem is this. So the first thing we have to do here is we have to write minus 64i in polar form, because our number has to be in polar form in order to use de Moivre's theorem. So if we think about what minus 64i looks like, well, remember that up here is I, the I-axis, so down here is the negative I-axis. So if we go really far down here will be minus 64i. And it can help to draw a little arrow just to visualize it. So remember that we always measure our angles from the positive real axis. So basically, when we're writing down our angle theta, we're going to measure it like this. So that's going to be theta will be equal to 270 degrees, or you could say 3 pi over 2 radians. Alternatively, you could also say minus 90 degrees, because you could kind of rotate this direction, and that's the negative direction. And equivalently, you could also say minus pi over 2. I'll go with degrees because people tend to just find degrees simpler. So that's our angle. And then r is the magnitude, so it's kind of like the length of this complex number. And clearly the length is just 64 because it moves 64 units down. If the complex number looked something like this green line, then you'd have to use Pythagoras' theorem to find the length of the green line. But here, it's just minus 64i, so obviously the length of that line is the length is 64, which is the magnitude. So that means that we can rewrite, instead of writing minus 64i, we can write that as the magnitude, which is 64. So that's our r value. So r is 64. And then we can have cos of, again, I'm just going to use 270 plus I sine 270. And it's a good kind of sanity check if you put this into your calculator and see what you get. So when you put it into your calculator, you should get 0 for this and minus 1 for this. So then when you multiply this together, you get minus 64i, which is this. So we know that both sides are the exact same, which means we've done it correctly. So now we can just rewrite, instead of minus 64i, we can write z to the power of 6 will be equal to 64 times cos of 270 plus I sine of 270. Now, before we go ahead and solve this, because we want multiple solutions, we kind of need to have multiple solutions here. Right now, there's only one value for the right-hand side, but we can actually add more values. And the way that we can do that is if we write it as this. So if we write cos of 270 plus 360n, and n can just be any number. Actually, I won't use n, I'll use m. The reason I'm not going to use n is because you might get confused about that. Because we use n for the power in de Moivre's theorem, so I don't want to confuse you. So we'll say n, and we'll have plus I sine of 270 plus 360m. And the reason we do that is because you can just add 360 onto any of these angles. So see this 270 here. If I go another 360, we still end up at the same point down here. So that just ensures that we're going to get multiple solutions when we do out our answer. So now we can apply de Moivre's theorem, because they do want two values of z. So we can do the power of a sixth on both sides. So we'll have z will be equal to, I'm just going to copy and paste this. So we're going to have this entire thing to the power of a sixth, 1 over 6. And then we can use de Moivre's theorem here. So if we have the whole thing to the power of a sixth, we can just do the r to the power of 6 and then multiply the power by the angles in here. So the way that we can kind of transform that is we'll have z equals, so we'll have 64 to the power of a sixth. And then what we're going to have is we're going to multiply that by cos of, and we're going to have 270 plus 360m divided by 6, or in other words, it's multiplied by a sixth, but I'm just writing it as divided by 6, plus I sine, and then we'll have, again, 270 plus 360m, all divided by 6. So 64 to the 1 over 6 is just equal to 2, and then we'll have cos, and you can put that into your calculator, and what you're going to get is you're going to get 45 plus 60m, and then plus I sine, and again 45 plus 60m. Remember that these are all in degrees. And then what we can do is remember that we could choose any value of m up here, so we can choose any value of m down here, and we just need to get two values. So we'll just choose, I guess the easiest one is m equals 0, which means that z will be equal to 2 times cos 45 plus I sine 45. And then we can also take m equals 1. Again, it doesn't really matter what number you choose as long as it's two different answers. So that will give us z equals 2 times cos 45 plus 60 is 105 plus I sine of 105. and we can just put both those into your calculator. So when you put these into your calculators, you should get root 2 over 2 for cos 45 and sine 45, and then you should get these things for cos 105 and sine 105. If you were clever, you could probably choose different values for m and get easier answers, but these are just the first two. So let's give it in our simplest form, C and D in surd form. So again, A plus, or C plus DI, where C and D are in surd form. So I'll take the m equals 0 first. So we can just multiply this 2 in, and what we're going to get is we're just going to get root 2 plus root 2i, and that's A plus BI, or the form C plus DI, whatever. So that's one answer, and then the other one we can say we'll have root 2 minus root 6 over 2, because the 2 over the 4 will cancel, let's just give us a half, and then we'll have plus, and then we're going to have root 2 plus root 6 over 2i. Again, multiplying that 2 into here, the 2 and the 4 kind of cancel down to give us a half, and here is our second answer. Again, it's in the form C plus DI, where C and D are in surd form, and they are real numbers.